Hello everyone, I'm Shivani and welcome to Civil Series. As you all know, we started a new series of short notes, and for short notes we choose a first subject as strength of material. In the previous video, we completed the elastic constants, then basic definitions and stress strain in detail. So in this video, we'll try to cover a remaining portion of strength of material. So here, the first point for today's video is beam. So you all know what is beam. So beam is an horizontal structural member which is present in each and every building construction. So this is an horizontal member which is called as beam. Okay. Beam contain two parts. If we cut this beam about its half or a mid span, about its length, then this is nothing but a neutral plane. This is nothing but a neutral plane. And if we cut this beam into a section, and this is the section of beam, if we take the half portion or if we cut this beam into the half, then this is nothing but a neutral axis for this beam. So neutral axis is for cross section and neutral plane is for the length or longitudinal section. Okay, so beam is nothing but a horizontal structural member or a flexural member, because in a beam bending happen, and beam carries a transverse loading. Beam carries a transverse loading along its neutral axis. Transverse loading. Transverse loading is nothing but a perpendicular to neutral axis. So this is the beam. Then next, type of supports. There are four types of support. First one is roller support. Roller support represent like this. This is the roller support, and roller support is with a single reaction which is vertical, means roller support resists the vertical reaction. Then second support is hinge support. So hinge support is represented like this. Hinge support is with two reactions. First one is vertical and second one is horizontal. Means hinge support resists the horizontal and vertical movement both. Then third is fixed support. So fixed support is represent like this, and fixed support has horizontal, vertical and movement, all the three reactions. Means it resists the movement of a beam in a horizontal, vertical and in a turning effect or like a movement effect. It resists all the three movements. Okay, all the three reactions in fixed support are resisted. Then third is guided roller support. Guided roller support. In the case of guided roller support, there are two type of support. First one is vertical guided roller support, and second one is guided horizontal guided roller support. The example of vertical guided roller support is horizontal, or the vertical guided roller support example is lift and shutter. And horizontal guided roller support example is horizontal horizontal sliding window. So these are the examples for the vertical guided roller support and horizontal guided roller support. Then next, type of beam. So there are six types of beam. First one is simply supported beam. So first one is simply supported beam. So this is simply supported beam, and simply supported beam is with roller support and hinge support. Simply supported beam. So first one is simply supported beam. On one side there is a hinge support, on another side there is roller support. Then next is overhanging beam. Overhanging beam has a two-side overhanging beam and one side overhanging beam, means one support is free. Okay, so this is the overhanging beam. Then next is cantilever beam. So cantilever beam means one support is with fixed support. One side is with fixed support, another side is free. So this is cantilever beam. Next is fixed beam, means both supports are fixed on both sides. So this is the fixed beam. Then next beam is continuous beam, means whichever the beam has more than two supports are called as continuous beam. So this is the continuous beam. Next is propped cantilever beam. Propped cantilever beam. So this is the propped cantilever beam. One end is fixed, another end is hinge or roller, whichever it may be. But this is the combination of cantilever beam, and here in case of cantilever beam, one end is free, but in case of propped cantilever, both ends are with support, but one end is always a fixed end. Then next part is static equilibrium equation. There are three static equilibrium equation. First one is summation of H equals to 0, means summation of horizontal forces which are on beam, summation of horizontal forces equal to 0. Second equilibrium equation is summation of vertical forces equal to 0. And third is summation of movement equal to 0. These are three static equilibrium equation, and on the basis of these static equilibrium equation there are two structure. First one is determinate structure and second one is indeterminate structure. In case of determinate structure, we analyze any kind of a beam with the static equilibrium equation. That structure is nothing but a determinate structure. Means the determinate structure is analyzed by static equilibrium equations, and second, indeterminate structure is not able to analyze completely by static equilibrium equation, not able to analyze completely by static equilibrium equations. Then second, SOM is depend upon determinate structure, because in case of SOM we deal with the structures which are determinate, means which are solved by static equilibrium equation, and in TOS we deal with that structures which are indeterminate, means not fully solved by static equilibrium equations. So TOS is for the indeterminate structures. And the examples for determinate structures are, or determinate beams are, simply supported beam, then cantilever beam and overhanging beam. Cantilever and overhanging beam. So these are the beams which are calculated fully by static equilibrium equations, and indeterminate are fixed beam, then next is propped cantilever beam, next is propped cantilever beam, and last is continuous beam. So these are the indeterminate structures which are not fully calculated by static equilibrium equation, because in these fixed propped cantilever and continuous beam there are reactions or number of unknowns are more than 3. Okay, so that's why we are not able to calculate the more than 3 unknowns by these 3 equations. So that's why this is under the indeterminate structure. And in case of simply supported cantilever overhanging, only 3 unknowns are there. But in case of overhanging, if there are a number of unknowns are more than 3, then also that overhanging comes into indeterminate structure. But but in case of overhanging beam the unknowns are 3, then we use the static equilibrium equation to solve that beam, and this consider under the determinate structure. And one most important point about the simply supported beam, simply supported beam, in that simply supported beam one end is hinge, another end is roller. If we take both the support as a roller, then that structure is unstable. Okay, and if we take that both support as a hinge, then also that structure is unstable. Okay, there are some rules for determining the stable and unstable structure. We discuss that rules in a further video or in a further slides. Next is type of load. So first one is point load or concentrated load. So this is the point loading or concentrated loading. Second is UDL, uniformly distributed load. So this is the uniformly distributed load. This is how it represent, and this is in, for example, this is in W per meter. Okay, and this point load is represented in Newton. Okay, this is not in meter or anything. This is directly in a Newton, and this is in Newton. Okay, we take it as W Newton per meter. Okay, this is how the uniformly distributed load, and here we need to convert this loading into point load. So here we convert this as a Newton. Okay, so for that, this is the length of this span, and for converting this, first take this loading as W and multiply this by length. Then this is the point load, which is WL. So here WL is nothing but a point load, and which is in Newton. So this is how the uniformly distributed load, and by using this point load you can calculate or you can solve the further calculation. And then next is uniformly varying load. So uniformly varying load. So uniformly varying load is represent like this triangle, and this is the length, and here we also need to convert this triangular loading into point load. But, and one more point, this uniformly distributed load is put on half of its length. Always put it on half of its length. And here in case of uniformly varying load, always put that point load is h by 3 or L by 3 from this base side, means h by 3 from here and 2h by 3 from here. Okay, so how to convert this? So first, this is the W. Here the loading is present, and this loading, take it as a triangle, and the area of this triangle is half of base into height. So first half into what is the base, this is W base, and divided by L. So this is nothing but a point loading for this uniformly varying load UVL, and put it on this point WL by 2. So this is how the type of loading, these are the three major loadings which are used in the calculation of bending moment and shear force. There are two important points, and there are very important points. We discuss that point in a further session or further slides, but this point is important, so I tell it here. So note that point. So first point is the bending moment at hinge. Bending moment at hinge is 0, means at hinge point the bending moment is always 0. And next, the point of contra-flexure occurs in overhanging beam. Point of contra-flexure. So we'll discuss all this point of contra-flexure and bending moment further session, in further session. But here remember these 2 points. The bending moment at hinge is 0, and point of contra-flexure occurs in overhanging beam. Overhanging beam. Okay, the next is first couple. Couple is that force which is equal in magnitude, but opposite in direction. But opposite in direction. And couple is itself a movement. Couple is itself a movement. First, equal in magnitude, opposite in direction. Second, couple itself a movement, and movement is nothing but a turning effect of a force. Movement is nothing but a turning effect of force. Then next point, turning effect of force. This is nothing but a movement. Movement is force into distance or force into perpendicular distance, and movement is also a couple. But in case of couple, the forces are equal in magnitude and opposite in direction. Couple is vector quantity. Couple is vector quantity. So in short, what is vector? Vector is nothing but the force which has a magnitude and direction both are vector quantities. Second, scalar quantities. Scalar quantities which has only magnitude, no direction. Then third is tensor quantity. So tensor quantity, first magnitude is there but directions are two in case of tensor. Then example for this tensor is stress and strain. So this is how the couple. And next is then shear force and bending moment. So shear force is summation of all the vertical forces. Summation of all vertical forces is nothing but a shear force. And bending moment is nothing but a summation of all the moments. Summation means addition. Addition of all vertical forces is shear force, and addition of all movements on a particular beam due to the vertical forces, horizontal forces and the movement, all the addition of these movements is nothing but a bending moment. Then second important point is sign convention. So sign convention for shear force are whenever the applied force is in vertically downward direction, take it as negative, and whenever it is vertically upward, then take it as positive. This is the sign convention when you calculate the shear force from left side of beam. And whenever you calculate from right side of beam, then take upward as positive and downward as negative sign. Okay, so here what is right side and what is left side? So right side means whenever you calculate the shear force from this point to right side, then take these sign convention, and whenever you start from this point and calculate in this direction, in left direction, then take this left direction sign conventions. The next sign convention for bending moment. So sign convention for bending moment are, first, this is the same beam. Okay, if you calculate the movement from right side, then take it as this side, then take it as positive. From this, take it as negative. Here the clockwise is negative and anti-clockwise is positive. Okay, this is the beam, and if you calculate the bending moment, if you calculate the bending moment from this point, okay, from this point in this direction, then take these signs, okay, these signs, then take these signs. And if you calculate the bending moment from this point in this direction, then take these sign conventions. Okay, this will be confused right now, the bending moment sign convention, but by using these sign convention, the steps to find out the bending conventions are more easier than by hogging and sagging, as my point of view. So you go through this, or if you want to know about the hogging and sagging, we will discuss that too. So whenever the beam has these kind of sign convention, whenever the beam has these kind of sign convention, which is like hogging and sagging. Hogging take it as positive, and hogging take it as negative, and sagging take it as positive. So these are the sign conventions for sagging. Okay, because of this force the beam get deflected downward side, so this is the sagging, and take it as positive. And if on this beam the direction of forces are like, or direction of movement are like this, then the beam get hog, and due to the hogging the take the movement sign convention as negative. So these are the hogging, sagging, and the sign conventions for bending movement. Then next is, okay, this is a chart for shape of shear force diagram and bending moment diagram. As you see, the shear force and bending moment, shear force is summation of all the vertical forces, and bending moment is summation of all movements. After calculating the shear force and bending moment, the work is to draw a shape of shear force diagram and bending moment diagram. For that there are some rules. For different loading there is a different kind of shape for SFD and BMD. So if in on the beam there is no loading, means no loading, the span is empty, then the shape of SFD on that beam is straight line. Okay, then the SFD for no loading is straight. For BMD the line is inclined, so here draw a inclined line for BMD in case of no loading. Then second, for UDL, for uniformly distributing load, the line is inclined for the shape of SFD, and 2D parabola, and 2D parabola for BMD. Okay. Then for UVL uniformly varying load, 2D parabola for shape of SFD, and 3D parabola for BMD. 3D parabola for BMD. The next loading is point loading. So for point loading, a vertical bluff means vertical line for shape of SFD, and there is no effect, in case of BMD. Same as in case of couple. In case of couple, there is no effect in SFD, but vertical bluff in BMD. So this is how we can draw a SFD and BMD by using these simple rules. Then next is, then there are some important points. Please note that points. First point is contra-shear, and second point is contra-flexure. So contra-shear is related to shear force, contra-flexure is related to bending moment. If shear force changes its sign, then that point is called as contra-shear, and if bending moment changes its sign, then that point is called as contra-flexure. Changes its sign means from positive to negative and from negative to positive. This is the conversion of shear force and bending moment diagram. Then one more point is important. If on any point shear force is minimum, then on that same point, bending moment is maximum. Bending moment is maximum. These are the important points. Remember these. And one more point is that the span on which shear force is constant. Shear force is constant, then that span is shear span. And if on any beam, if bending moment is present, if only bending moment is present and there is no shear force, then that condition is pure bending condition. So all these points are important. The next point is important cases in overhanging beam. There are two conditions in overhanging beam. First condition, the whole span is L, and the span from this roller support to end is A, and from this hinge to end is A. So remaining is L minus 2A. And in second case, the total span is A plus L plus A. Okay, L plus 2A is a total span. These are the two conditions in case of overhanging beam. So here we see what the value of A for different conditions of or different length conditions. Okay, in first case, the bending moment is positive bending moment is equals to negative bending moment. First, maximum positive bending moment is equals to negative or maximum negative bending moment. This is the condition. Okay, in that this condition is nothing but a economical beam. This is economical beam. This is first condition in case of case 1. If that condition happens, means the bending moment is like this. Means positive and negative bending moment are equal. In that condition, A is equals to 0.207 of L. This is the value of A. And they directly ask this kind of beam they given, or they ask that maximum positive bending moment equal to maximum negative bending moment in case of overhanging beam. A is equals to what? So A is equals to 0.207 L in this case. Second case is total negative bending moment. Total negative bending moment. So total negative bending moment diagram is like this. Means total bending moment part is in negative case. So this is the BMD and value of A is L by 4. So this is the value of A here. Then second condition. In second condition, you see the value of length A, L and A. Okay, here the value of A is equals to L divided by 2 root 2. So these are the different values of A for overhanging beam with different length conditions, with different bending moment conditions. And this is the important question. Important question. Remember this question and values of A for different conditions. Relation between bending moment, shear force and load intensity. Derivative of movement is nothing but a shear force. And derivative of shear force is nothing but a minus of loading. So this is the relation between shear force and bending moment and load intensity. Then there are some extra points. So here we discuss the weight comparison between square, rectangle and circle. So the weight of rectangle to the weight of square is equals to 0.79, and next the weight of circle to weight of square is equals to 1.11. So these both are important values, and this question is also asked in exam. So next question or next point is, then second extra point is, here the square section is given. In the first figure a square section is given, and in second figure same that square section with same weight and same area. But in first figure the sides of the square are horizontal and vertical to the given line, and in second figure the diagonals are horizontal and vertical to the given line. Okay, and here we need to find the moment resistance for both of the figures, and the moment resistance for first figure represent as M1. This is M1, moment of resistance for first figure, and moment of resistance for second. So ratio of moment of resistance is moment of resistance of first, means the square which has horizontal and vertical sides of square, the moment of inertia of first is larger than the second, which is by root 2. Okay, so M1 is root 2 times larger than M2. Means moment of inertia of first square is larger than the moment of inertia of second. Then the next point is flattering section. flattering section. In that flattering section, we cut the uppermost part of any figure. Here first figure is with diamond shape and second is for the circular figure. So in case of diamond shape, we cut this a by 9, means total is 2a, side is a. Okay, so here this is a up to this point, from top to here the value is a, and this cutted portion is a by 9 and remaining portion is 8a by 9. So this is the flattering section for diamond, and by cutting this dash part from top and bottom, then strength is increased by 5.37%. Strength increase by 5.37%. Same in case of a circular section, if we cut this part called as, and cutting of this part called as flattering, and if we cut this part from top and bottom as 0.011d, diameter of 0.011d, then the strength is increased by 0.7%. Strength increased by 0.7%. Okay. The next fourth point is strongest beam from circular log. Strongest beam from circular log. Here we cut a rectangular part or rectangular beam from a circle and then find out the values for it. Okay, here we consider this is the circle and we cut a rectangular portion from this circle. Okay, this section here, h is the height for rectangle, b is the width for rectangle, and d is the diameter of this circle. Then here the values of h by b is equals to root 2. H by b means what? Height of height of rectangle to the width of rectangle ratio is root 2. Then d by b, the ratio is root 3, and then h by d, the ratio is root 2 by root 3. So these are the three values, and all the three values are important, and this question is mostly asked in the exam. Then next is slope, deflection and movement chart. So in that, first is the cantilever beam with UDL, second cantilever beam with point load, third cantilever beam with UDL, fourth cantilever beam with UVL, then fifth is simply supported beam with point load, and sixth is simply supported beam with UDL. Okay, movement of these beams are first movement. First, here in the cantilever beam there is only movement, so movement is m. Second WL, third is WL square by 2, fourth is WL square by 6, then fifth is WL by 4, then sixth is WL square by 8. Okay, these values you need to remember these values. And for slope and deflection there is a one trick, which is for slope, the slope represented by theta. Okay, so here for first ml by ei, then for second take ml by 2 ei, then for third take ml by 3 ei, then for fourth ml by 4 ei. Then reverse for simply supported. Theta equals to ml by 4 ei and then theta equals to ml by 3 ei. Just put the values of movement into the m in this theta equation. So you get the values of slope. And then next, in case of deflection, so in case of deflection the values are delta is deflection, theta is slope. Just multiply that theta with L by 2 for first condition, then 2L by 3 for second condition, 3L by 4 for fourth condition, 4L by 5 for fourth condition. Then for simply supported, multiply by L by 3, then for fifth or sixth condition for UDL, multiply by 5L by 16. Okay, so these are the deflection value. Just put the values of theta into this and multiply with the factor given here, so you get the values of deflection. So these are the deflection and slope chart. Then next is distribution factor. Distribution factor is a ratio of stiffness of that member to stiffness of that joint. Distribution factor is stiffness to summation of stiffness ratio. This is the distribution factor, and distribution factor in case when far end is fixed, then the stiffness is 4 EI by L, and if the far end is hinge, then stiffness is 3 EI by L. Okay, these are the values of stiffness. Then next is fixed end movements. Okay, then next is fixed end movement. In the first condition of fixed end movement, the beam is subjected to point load at its center, and for that fixed end movement about A support, that is MAB, movement at AB is minus WL by 8, and for fixed end movement at MBA, means at the support B, is plus WL by 8. Then same for second condition. Here also point load is given, but that point load is on a eccentric loading, means on the left side the span is different and on the right side the span is different, and this is the formula to calculate the fixed end moment for the support A and B. Then third condition, fixed end moment for the beam which is subjected to UDL for whole span. Fourth condition, subjected to UDL but about the span A. Then next condition, subjected to UVL about whole span. Then next condition, subjected to UVL up to span A. Then seventh condition, UVL on whole span but in triangular portion or in a triangular condition. Then next, subjected to movement about the beam or the fixed beam, subjected to movement about its center, and next subjected to movement, but this movement is eccentrically acted on this beam. So these are the fixed end movement for the support A and for support B, and these all the fixed end movements are important, and most of the questions are asked from this part. So from first, then third and fifth, and this second, these are the four conditions. The four formulas are important. Where, and if you want this whole chart of slope and deflection and fixed end movement, so if you want that whole chart, then just comment down. I will put that chart into description if you want.